This is the solutions video for the week 4 free response dealing with circular motion. So we have a spacecraft of mass m in a clockwise circular orbit of radius r around Earth as shown in the figure above. And it looks like that radius r is from the center of Earth, which is what we want. Because remember, if it tells us the distance above the surface, we need to take into account the radius of Earth of r, or the radius of Earth as well. But for us, this is already from the center of Earth, so that is good. So on the figure, or in the figure below, draw and label the forces, not components. So we need forces that act on the spacecraft. Each force must be represented by a distinct arrow. Okay, so some forces I might need to include: tension, gravity, friction, normal force, things like that, applied forces. There's no strings in our spaceship Earth system, so not tension. We're not on a surface, so that automatically gets rid of friction and the normal force. So that pretty much leaves only gravity that could be acting on this spaceship. Okay? Gravity is an attractive force, meaning it's going to pull the two objects together, or in this case, pull the spaceship in a circle. Okay? So we're drawing the force of gravity on the spaceship from Earth. So we're going to draw an arrow, and it says draw and label. So I'm not only going to draw the arrow, but I'm going to label it FG of Earth on spaceship. So FGES. Okay. Now, some of you might be thinking, why aren't you drawing a centripetal force? Well, remember, centripetal forces are net forces or total forces. And we don't include net forces or total forces on free body diagrams, just the individual forces acting on the object. Okay. One thing that I also want to include here is if the question had asked me to draw the force acting on, looks more like a fish than a spaceship, but it's okay, the Earth from the spaceship, I would need to draw an arrow in the opposite direction, okay, but the same magnitude. So the magnitude of the force of the spaceship on Earth is equal and opposite to the force of the Earth on the spaceship, okay? The reason why the spaceship moves in a circle and the Earth does not is the spaceship has much, much less mass and therefore has a larger acceleration. That has nothing to do with the problem, but I just wanted to go over it. So let's take a look at the answer for A, make sure I got all my points. Okay, so I get 1 point for an arrow directed towards Earth's center. Awesome. And I get a point for the correct label. Good. So again, you're getting a point for that labeling. So it's really important that if it says draw and label, that you label. Okay. So what you should do is highlight, underline something, the action verbs or the action words in the sentence, because that's going to tell you what you need to do. Okay. So then we have BI, derive an equation for the orbital period of the spacecraft in terms of little m, the mass of the Earth. So this m is the mass of the spaceship, mass of the Earth, the radius, and physical constants. Okay. As appropriate. If you need to draw anything other than what you have shown in part A, do not draw it on part A. So physical constants, what that is going to mean is big G, the gravitational constant, and little g, the acceleration due to gravity on the surface of the Earth. We're not on the surface of the Earth, so we should definitely not be using little g. Okay? There are other constants on the front of your reference table, but the only one that we should need is big G. Okay, so our action verb, what we need to do is derive an equation. Okay, and what we need to derive an equation for is the orbital period of the spaceship. And we need to derive it in terms of M, E, R, and G, meaning those should be the only letters in our answer. Okay. Now, the orbital period of the spacecraft is just the amount of time it takes to go around the Earth once. Okay. So it's essentially a time. Now you might be thinking, oh, awesome. The reference table has two period equations for us. They're labeled TP and TS. It's 2 pi square root L over G and 2 pi square root M over K. But here's the thing. This period here is for the period of a pendulum. An Earth and spacecraft system, definitely not a pendulum, so we can't use that. TS is the period for a mass on a spring. An Earth and spaceship, definitely not a mass on a spring, so we can't use that. So then I have to think, okay, well, what other period equations do I have? Well, I know on the reference table I have period as 1 over the frequency, but I don't have the frequency, so I can't use that. Okay. The one thing that you have to remember is that when these objects are orbiting in circles, specifically when they're orbiting in circles at a constant velocity, we can say that the speed of that object moving in a circle, which I say is VC, is the circumference of that circle, 2 pi r, over the period. So this is an equation that you do have to memorize, okay, or keep in mind, because it's the hidden way that we're going to find the period, okay? So rearranging that for period, I'm just going to continue my work over here. I have period is 2 pi, r is the radius of the circle, so that's a big R, over VC. So R is good, I can keep that, but V is not good. So I now have to think about a way to get the speed of an object moving in a circle. Okay. Well, if I look at the reference table, I have the equation AC is V squared over R, where this V is the speed of the object moving in a circle. So I'm sticking to my equations with the subscript of C. Okay. But in order to know an acceleration, I need to know a net force. So this is when we would use the centripetal force. So we would say the net force, FC, is MAC. Okay. Well, the only force acting on the spaceship is the force of gravity between the Earth and the spaceship. So that means the force of gravity between the Earth and the spaceship is the centripetal force. Also, if you hear rustling, my cat is playing in a box right now. Okay, so then we have M, and this M here is the mass of the spaceship, since that's the thing doing the acceleration for this equation. And then we have AC. So you might be thinking, all right, well, I have two FG equations. I have the easy one, FG equals mg, and I have g m1 m2 over r squared. Well, this one is great if we're on the surface of a planet or we need to find the acceleration due to gravity. We don't need any of those things, so it doesn't make sense for us to use this equation. So I'm going to use this one. So big G is that universal gravitational constant. It doesn't matter what mass you say M1 or M2 are, Earth or spaceship. Doesn't matter because multiplication is commutative. So we have a little m, big M-E, over r squared. And remember, the whole goal of this is to solve for this v. So instead of having an AC there, I'm going to plug in v squared over, and I'm going to use the capital R since that's our radius variable. Okay, so now I want to see if anything can cancel left and right. And lucky for us, it does. The mass of the spacecraft cancels out, which means that the mass of the spacecraft isn't going to affect the period. So if I doubled the mass, tripled the mass, half the mass, the period is going to stay the same. Okay. Also, one of the r's ends up canceling. Okay, so remember, an r squared is really just an r times an r. So one of those r's ends up going away. All right, so I'm left with GME over r is v squared. So that means v is the square root of GME over r. Okay. So the period is going to be 2 pi r over square root of GME over r. Okay. Another way to write that might look a little bit better is 2 pi r square root of r over GME. Okay. Or you could also write it as 2 pi square root of r cubed GME. All of those answers should be acceptable. Okay, what matters is the way that you get them. Okay, so let's just check and make sure I only have variables I need. Okay, so M, ME, R, and G, I only have an R, a G, and an ME. Perfect. Okay, just because they list a variable does not mean it needs to be included in your equation. They're just saying you could have this. That's what this as appropriate means. So let's go ahead and check my solutions to see if I get all of the points. Okay. So this is a 3-point question. So the first thing we need to do is using or implying Newton's second law, the idea that the net force is ma, and equating centripetal force to gravitational force. So I did that. So I said Fg is mac. Gravity is the centripetal force. So I got that point. Okay. For explicitly or implying and determining the speed of the spacecraft, I did that. Okay. That is this first step that I did here. And then for a correct answer algebraically. Okay, so this is equivalent as well. They just stuck the 2 pi back under the radical, whereas I left it out front. So that is correct. Okay, or you could also leave it in terms of t squared if that's what you ended up getting your answer as. Okay, so I got all 3 points for that. Okay. The next part of this is it says a second spacecraft of 2m. So we're changing the mass of the spacecraft. Is placed in a circular orbit with the same radius r. Is the orbital period of the second spacecraft greater than, less than, or equivalent to the orbital period of the first? So we're looking at this equation. And if I look at this equation, the mass of the spaceship does not show up anywhere in this equation. All that does is the mass of Earth, which means if we change the mass of the spacecraft, the period is not going to change. So this is going to be equal to. And then we have to briefly explain our reasoning. So we can kind of just say that. The period of the spacecraft only depends on the mass of Earth as shown in the equation above. Okay, so you can, it doesn't say don't reference equations or anything like that. You can reference the equation that you got. Okay, now let's say you got this equation wrong. Let's say you, I don't know, there was for some reason an m in there. If you answered part 2 based on your equation from part 1, and you referenced your equation from part 2 in your explanation, you could still get partial credit for part 2 based on your incorrect equation. Okay. So if you are not the greatest at deriving equations, that's okay, as long as you can get this briefly explained part. Okay, so let's make sure I got all my points there. Okay, it's a 1 point. I don't get any points for saying equal to. My points come from a correct explanation that the period does not depend on the spacecraft or only depends on the mass of Earth and radius of orbit, which I said. And again, here, it says, or an explanation consistent with the answer from B1. So again, if you had gotten the equation wrong from B1, you could still get credit for B2. All right, and then part C. So this last part. The first spacecraft is moved to a new circular orbit that has a radius greater than r. So we've increased r. Okay. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? Okay, so the speed equation that we had gotten previously is v equals the square root of g me over r. Okay. So what that means is that v and r have an inverse relationship. Okay. So if we increase r, v is going to decrease. Okay. And you can think of it in a few different ways. You can think of it referencing this equation. You can think that as r increases, the force of gravity is going to decrease. So the acceleration is going to decrease. So the velocity must also decrease. Okay. You cannot, however, use the equation v equals 2 pi r over t to help with this explanation, okay? Because remember, this t function down here also depends on the period, like we showed right here, okay? So since that's the case, this would not be a good equation to use. You want to see how v directly relates to something that is also not changing with the radius. All right, so briefly explain your reasoning. Again, what's great is we can use that equation from B1. So in B1, it was found that v is the square root of GME over R, meaning as R increases, v will decrease. Okay. It's just a brief explanation. It doesn't need to be a paragraph. One sentence is fine. So let's make sure I got that point. So I get no points for selecting less than, okay? But if the wrong explanation is selected, your explanation is not graded. So if you pick greater than or equal to, you can't get any points, unfortunately. So for a correct explanation of why the speed decreases with increasing orbital radius, I did that. Their example is the derivation in step B1 shows that speed decreases with increasing radius. Okay. All right. So that is it. Excuse me for this free response problem. Have a great rest of your day.